All right. So what we're doing here, guys, this is very important that you understand how to do all of these problems, because for our whole entire chapter 15, you still have to remember this. They still come into play. And by the way, just to make sure that everybody is clear on the pacing for the next couple of weeks, we are going to spend 3 days on chapter 15. So you're going to have a quiz on chapter 15 next week, Wednesday. We are going to spend 3 days on chapter 16. So you will have a quiz on the 21st, which is a Thursday. Then that following week is Thanksgiving. I know. All of your classes are probably giving you tests and quizzes. You will have a test on Monday. But there's a very important reason for that. Yes, that is not next week. That is the 25th. The reason for that is I'm terrified right now as to how much y'all have forgotten over a 4-day weekend. I think the worst thing that we could do is have a 5-day weekend and then come back and take a test. So I'd rather you guys have the best chance for success possible. Also, did I mention to you guys about the email I sent out? I did. Okay. I get my classes confused. All right, good. So we're okay on that. Let's take a look at the answers for this. By the way, I do have your quizzes graded, and I will give you those back at the end of class. We should have plenty of time to go over them. Okay? All right, here we go. Let's take a look at the work and the answers for this. So here is my work and my answers. For number 1, since our probability changed depending on if we hit the snooze button or not, a tree diagram. And really, the tree diagram is the majority of your work here. If I ask you, or if any quiz or test asks you to draw a tree diagram, you must do that. Points are associated with that. Large number of points on the quiz were associated with the tree diagram. Okay? So when we're talking about the probability of late, that means late with the snooze button or late waking up on time. Take those two values, add them together, your probability is 0.22. Probability of hitting the snooze button, given we knew you were late, is the probability of both of them, snooze and late, divided by the probability of late. So snooze and, you already calculated the probability of 0.8, and so that's what that gives me. And for number 3, there are so many different ways that you can do this. If you are talking about writing them in statement form, which you will need to do for your definition of independence, you need to make sure that that first letter always matches. And what you can do is you can start with the box itself and figure out those and then talk about what you're comparing. Thing is probability of female is 212 over 452. Female given index finger, that's 78 over 123. You want to make sure that it makes your box. Once you have that box, it's your choice how you set this up. I could have done probability of female, 78 over, probability of female, of index finger given female, 78 over 212. Probability of index finger in general, or it could have gone this way, but you should always see a nice 4-square box. It's a pretty pattern. And then you can't just write this. You actually have to say that it's not equal, so somehow indicate that they're not equal, therefore they are not independent. Is that what your question was going to be?
No, it's just
Little moments. Thank you. I did the math right. I just didn't write it down right. Thank you. Okay. Questions on those? Maybe kind of sort of remember doing this? Teeny weensy itsy bitsy bit? Y'all good? Okay. It's very important. We're going to be doing all of these things today. We're going to be using all of those today. All right, so, come on. Move it along. Hop along, little doggy. What we're talking about, chapter 15, is random variables. Let's think what that talks about. What does the word random mean?
no bias.
Okay, so, no. on both of those. Random does not talk about equal chance. It doesn't talk about no bias. Random means, right, we have all of these different outcomes that could happen, and I don't know which one will. That's the big thing about random, is there is nothing steering me to one answer or another. Okay? Variable. What is a variable? Okay, x is a good variable. What does x do? Change. Variability, variables all talk about change. So here we're talking about things that can change that we have all sorts of different outcomes for, where I don't know exactly what that outcome is going to be. That's what random variables are all about. So, nope, this way, or this way. Good. Okay, keep going. So basically what a random variable does is it's going to assume a value. And basically what that means is my outcome is going to be one of these set possible outcomes. And we are starting now where I'm going to start getting really kind of fussy about notation. Okay, I haven't done it up to now because I'm focusing mainly on big ideas. But from this point on, now that we've talked about random variables, you need to start talking about defining what your variables mean. So in this case, I use x a lot. I've seen textbooks that use y a lot. I've had professors that go either direction. I don't care what variable you use. But when you have a capital letter, that capital letter represents all possible outcomes for that event. Everything that you could possibly do. The capital letter is all outcomes. So if my outcomes are talking about grades, all possible grades, I would have A, B, C, D, F. Those would be all possible outcomes, and the X represents which of those you get. And then what we're going to do is we're going to talk about specific outcomes. All possible, capital X. One specific, lowercase x. Or y, or whatever you want to use. But capital versus lowercase. And I know X's, it's kind of hard to tell which one you're using. Y's, it's kind of easy. Maybe that's why a lot of people use Y's. And I don't care what variables you choose. If you're talking about grades and you use the variable capital G and lowercase g, more power to you. I don't care. Makes me happy either way. But there are two types of random variables, and some of you have already seen this because I'm a dork and wasn't careful enough about assigning Khan Academy problems. You have seen these words already. First type, discrete. Discrete basically means that you have a limited number of outcomes. That's what the term countable means. I can count and talk about each specific individual. For example, a discrete random variable would be shoe size. You know that there's tiny numbers up to big numbers. I just like to think of it are the ones that involve me. 8, 8.5, 9, 9.5. Discrete. You're not going to be able to walk into DSW and say, I'm looking for a size 8.34 shoe. That would be really, really cool. Custom shoes just for your foot. But they don't do that. Do you understand why that's discrete? It's one or the other or the other. You don't get an in-between value. Versus continuous. And we've been dealing up to this point about continuous random variables. Continuous random variables means you have a whole range and it can be anything within that range. Your grades are continuous random variables. Your grade can be anything from a 0 to 100. And sometimes more than that. For those show-offs. Okay? So discrete basically means boom, 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 boom. You've got a set. It's either this or it's not this. You don't have a range. Continuous is a range. And we've already been dealing with continuous because remember we were talking about length of pregnancies. There's a big continuous spread of that. Weight, that's a continuous spread. When we are talking about continuous, it's very easy for us to use, when appropriate, the normal model or your interquartile range and all of those things to describe and calculate things. Discrete tweaks it a little bit. So we've already talked about continuous random variables. Chapter 15 is focusing primarily on discrete, when you have specific outcomes that are possible. It's like if you're going to play a game, you can lose $5, come out even, win $5, win $10, win $100. You're not going to walk away from that winning $50.23. It's not an option. That's why it's discrete. So far, so good? A little good. All right, probability models. And today we're focusing on center. A probability model, to me, it's basically, you can do it in a picture, which is my favorite way to do it because it's organized, I can see what's going on. Or you could just calculate it. But a probability model consists of two main things. All of the possible values for your random variable, so what could your outcomes be? If I'm talking shoe size, I could have 8, 8.5, 9, 9.5. Those are my outcomes. Okay? But then we also have the probability that each of those individually occur. So I draw it like a table, where I'm going to have the top line of my table, my first row is going to be all of the possible outcomes, and the second row, matching up with each of those, is what is the probability of that outcome. Just kind of keeps it neat and simple. And then there's this. Just going to let you kind of sit on that for a second. Figure out what that means. Summing the products of each possible value by the probability that it occurs. Head explodes. Let's take this one thingy at a time. What is that? Mu, mean. Okay? Not a classroom full of statistic cows. Mu. Mu. That was funny. I got a little clap there. Okay, good. So that's a mu. That means mean, or what's another word for that? Average. Okay. This capital X, what is that? All of my outcomes for my random variable. I use this notation, this E of X, when I'm talking about discrete variables, when there are just set specific outcomes. So the expected value of X is talking about out of everything that could possibly occur, everything that you could have, what should the really long run average be? What can I expect? That doesn't mean that you are going to be getting that specific value. Just is talking about if I were to find all of the things that ever occur, what should the average in the long run be? Do you know what this symbol is called? It stands for sum. It's called sigma. That capital sigma symbol is talking about sum. And what are we taking the sum of? This lowercase x means the individual outcome times p of x, the probability of that individual outcome. It's a lot harder to write than it is to actually do. And this is one of those formulas you can see over here where we are on our little swing of things. We are here. Today we're talking about these two. I don't care if you remember the formulas or not. They're going to be given to you. I don't use them. I might use expected value because that's actually easier to do, like working it out, than it is to do it in the calculator. Like one of the few things. But we are going to be talking about standard deviation a little bit more later. But this is the expected value formula. You want to make sure before you even begin, before you try to find your expected value, do you have a valid probability model? If it is a valid model, what should all of your probabilities add up to? 1. And each of your individual probabilities should be not just less than 1, but between 0 and 1, because you can't have any negatives. So you want to make sure that that's true, because I'm telling you right now, I'm letting y'all know where your mistake is going to fall for this. People generally forget to make sure you have all outcomes possible. Like I could be talking about the most common shoe sizes, and I can be saying 7.5, 8, 8.5, 9, 9.5. Look at that window. But those aren't all of them. So I will need probabilities for less than 7.5. I will need probabilities for greater than 7.5. I have to make sure that all of those probabilities add up to 1. It's hugely important. And they're not always going to spell out each of those. And sometimes we're going to have to use our rules that we had from 13 and 14, chapters 13 and 14, to actually calculate what the probabilities are. We're going to see a lot of that today. Then there's the measurement of spread. What things do we have that measure spread? IQR. When do we use IQR? When data is skewed. IQR is skewed or not symmetric or not unimodal. What else do we have that measures spread? Range and standard deviation. Range is okay, but it's so sensitive to outliers, it doesn't always tell us that much. When do we use standard deviation? When it's symmetrical and unimodal. So for this case, when we're talking about spread, we're actually tacking in a new little word. Variance. Wait a minute. We've been using the word variance, right? What does variance talk about? Spread. Variance means how far are you from what you predicted? Variability. The amount that you are off. This is the formula for variance. And it's also up there. I really don't care if you memorize that. Personally, I never use it. Who are my AP Bio kids? Taken it or are taking it? How many of you have taken it? Do you remember calculating those by hand? Standard deviation and variance by hand, these long tables. You don't have to do that in here. 100% true. I remember that I took, and I believe the title of it was Calculus-Based Statistics in college as an undergrad. I passed it. I hated it. That's all I remember. It literally blocked like the entire experience out of my head. And the reason why? I could not, for the life of me, get these values correct when doing it by hand. I can handle this really complicated problem, but ask me to add 2 plus 3, I give you 6. Because I just do. I don't know. That's where my mistakes are. We're not doing that in here. AP Statistics is focused on understanding why, not doing the specific ins and outs of it. Okay? But I have bad news for you. If you end up taking statistics in college, that was pretty emphatic, throw my pencil, gosh darn it. If you end up taking statistics in college, you will have to calculate those by hand. Because they're evil. It's just the way they are. Every single one of my statistics classes in college, undergrad or graduate, they always made us calculate it by hand. Sucks. But hey, while you're in here, you don't have to. So what does that mean to you? What should you aim for? A 4 on the exam, or a 3 or better based on where you're going and what you're trying to get out of. Because y'all don't want to do this by hand, especially not if you're like me and you had one of those really evil professors who gave us a list of 20 numbers for a test and you had to calculate standard deviation. Ah! Oh, heck no. Okay, this is so much better. So the thing that I do need you to understand here, this is not going to be given to you. This is an extremely important relationship. And that is that there is a tie between standard deviation and variance. You can look at it either way. You can say the standard deviation is the square root of the variance, or the variance is the standard deviation squared. Both of those have their uses. The standard deviation we use when we're talking about the normal curve, when we're trying to talk about, get an actual idea of what this spread means. Unfortunately, we can't necessarily use standard deviation in all of the different formulas that we're going to have. Variance is the guy that we're going to use in our formula. So you need to understand that relationship, plus the fact that your calculator is not going to spit out variance. Your calculator can spit out standard deviation, but it won't spit out variance. So if I ask you for variance, what are you going to do? You're going to find standard deviation squared. Okay, it's very important. So I don't care how you choose to do this. If you're one of those like people, I'm going to do it all by hand because I can and I will. Okay, you're just weird. And you probably will run out of time, but that was your choice. We're just going to do it on the calculator. Expected values, if all I'm looking for on a problem is an expected value, sure, I'll do it by hand because it actually takes less work than it does to type it in the calculator sometimes. Okay? All right. So this is an example of two separate probability models. This is what I'm looking for. This guy is, hey, look, it's problem number 1, which basically means it's as easy as it gets. So for this problem, I've stripped, there's no context, it's all gone. Typically what you will see is I will write an x up here and I will say what it equals in context. I'll define my random variable. So these are my outcomes. These are my possible choices for x, 10, 20, and 30. This is the probability of each of those individual things. The probability of 10, the probability of 20, the probability of 30. Okay? Just a nice, clean way to display this. What we want to do here is we want to find the expected value for each of those. That doesn't mean I'm telling you exactly what's going to happen when I run this, but in the extreme long run, what could I expect to occur? So how do I find, and again, when we're using discrete variables, we typically look like that. The expected value of all possible outcomes, that's a capital X. How do I calculate this? It is the sum of all of your products. So that means I'm going to take 10 times 0.3 plus 20 times 0.5 plus 30 times 0.2 off the screen. That's all you do. And you can do this by hand. You can do it in your head. I'm going to be amazing. I'm going to do it in my head. 10 times 0.3? 3. 20 times 0.5 or half of 20? Boom. 30 times 0.2 or 3 times 2?
6.
So that means the expected value of x is in fact 19. I want y'all to do part B for me, please. Do the B, do the B, do the B, baby. I know that was weird. Whatever. That means that if, for example, like let's say that this was a game, and each time I played the game, I had the outcome of getting 10, 20, or 30 points. If I were to play this game forever, the average score out of all of my games should be about 19. Okay? I think the more that we'll do it, that'll put the context in place for you, you'll understand a little more. Let me keep. Basic computations here shouldn't be too long. Okay, what did you get for 1B? 4.2? 4.2. Beautiful. You can put the 0, you cannot put the 0, I don't care. Now, to show you how to do these on your calculator all at once, because this is not that bad when you only have a very limited number of outcomes. But if you're like me, you're likely to make little mistakes. How can I do this on the calculator? It's actually quite simple. You're going to go to your Stat button, Edit, clear out whatever you have there. If I accidentally hit Delete and my whole list disappears, what can I do? One more time. Okay, that's a lot more work. It's actually a lot easier just do Stat, Setup Editor, Enter, Enter. And what's nice about that is sometimes you'll accidentally delete a list, but you'll want all that other information. You've got other stuff stored. This will bring that all back. You'll have to start all over again. So again, if you accidentally delete, just do Stat, Edit, Setup Editor, Enter, Enter. Okay. So what I'm going to do is I'm going to look at Part B. I'm going to go to my Stat, Edit. I'm going to put in my first column my first row. So I'm going to do 2, 4, 6, 8. And then in my second column, I'm going to put my second row. Oops. Make sure you type it in correctly. Probably would have hated stats because I can't even type things into a calculator correctly. I'm special. Now, before, when I asked you to calculate mean and standard deviation off of a basic list, what would you do? Stat, calc, 1var stats. Guess what we're doing here? Stat, calc, 1var stats. Same exact thing. The only part here that's different is we obviously still have my list of values in list 1, but now we have a frequency list. That frequency list is list 2. And if you want to change that number, you'll look here, you'll see all of your L1, L2, L3, those are all in blue. So just by doing second 2, that will type in list 2. And there you go. Just like we calculated, here is my average. Either way, that's good. These things we would use for other calculations, but we're not going to. As for standard deviation, the only thing that I'm going to ask you to do is read it off the page. Read it off the screen. Okay? So you could have found the standard deviation for this, and the way you just would have written that is you would have said standard deviation of x, and you would have said 1.887 or 1.89. So, pretty clear and easy to understand. I just think that if all you're doing is expected value, if you can just type that in, add, multiply, add, it's almost quicker than doing the stat, 1var stats, calc, enter. Okay? All right, this stuff gets more complicated when we start throwing in actually having to create the probability model yourself. So I'd like you guys to read what this problem is talking about. See if you can kind of get a general idea of what's going on here. And I had folks in the other class bring up the fact that they're still really struggling with what a deck of cards is. I have no problem. If you go to Google and you Google deck of cards and you pull up an image and you print out that image on a piece of paper so you have what a deck of cards is made up of, you're welcome to do that. I'm not going to do it for you because I can only print in black and white, and that kind of defeats part of the purpose. Okay? So if you want to do that and then bring it in to use on tests and quizzes, it just will have to be clear of anything else. The only thing that can be on that page is your pictures of a deck of cards. Does that make sense? So if you would like to do that, you're more than welcome to. All right. What we're going to do here is we are going to generate our probability model. When I do my probability model, I have a top row and a bottom row. The top row is all possible outcomes. What am I interested in as my outcomes here? Money. So specifically, I'm going to talk about this as being my, let's just say amount 1. And you know what? I'm going to put a $sign there. Underneath that is going to be the probability out of all of the amounts that you can win, you win that specific value. So capital X, lowercase x. Now you got to be really careful. All of the possible winnings. What's the smallest amount that I can walk away with? 0. It's possible to have no money. What else could I have? $5. Okay, what else could I have? $10. And one more time? 30. Beautiful. Thank you for not saying 20. That is the first thing. Understanding what your possible outcomes are. Now, when we're creating our probability model, you need to make sure that I can tell where your answer comes from. I think it's easier just to do fractions. So in order to get $0, what has to happen? It's a red card. How many of the cards are red? Okay, in order to get a $5, what do I need? A spade, and how many spades are there? Now, I'm lazy. There are a certain set ways that I can get 10. 10 is going to be the one that's the worst to calculate, so I'm going to go straight to 30. What do I need to win $30? Ace of clubs. How many of those are there? Just 1. So that means whatever is left is just what do I need to take it to 1. So I've got 26, 13, 1. I need 12. Does that make sense? All cards present and accounted for. This all adds up to 1. So this has a sum of 1. I need to see these things because if you just give me a decimal, number 1, it might be a rounded decimal. Maybe you just rounded it wrong. Number 2, for some of these guys, you actually have to use your probability rules to calculate it. I need to know how you calculated that number. It didn't just magically appear on your paper. Makai, you want to wake up? Makai? If you're having trouble, stand up. Okay. All right, so what I'm looking for here, I've done my probability model. Now I want to find the expected amount that you'll win. I don't care if you do that by hand or on your calculator. Just do it. Calculate that. Figure it out. What do you get? Sage, did you get it? You just looked like you were done, that's all. Henry, did you get it? Anybody get the answer? What is it? 4 point. What is this talking about? This is talking about dollars. So what should you round to? 2 decimals, the hundredths. And ladies and gentlemen, you need that label is hugely important. You need to have that. You don't have that, you don't have context, there's a lot of your points gone. Secondly, you need to be thinking in terms of that context. Money should always be rounded to the nearest cent. Other things, if we're talking people or houses or cars, we're not necessarily gonna round because we're not going to get into the philosophy of all that stuff. What does this thing represent? What? Lunch party? I'm hearing weird things. Not a clue. Okay, so what is this? What does that represent? The amount of money you can expect to win. So if I play this game, I am safe to expect to win $4.13. I can't win $4.13. It's not one of my options. I can win 0, 5, 10, or 30. So refine that a little bit. It's the average in the long term. Understood? If I were to play this for infinity and beyond, that's what the average of each game's winnings would be. Now, can you use that to tell me what you would be willing to play or pay to play this game? What would you be willing? Less than $4? 13 cents back. Anybody else? So, I mean, technically, if you want to make sure that you come out ahead, you should be willing to pay anything less than that, right? So most people would want, we would want anything less than $4.13. If this was an actual casino, what do you think the cost of this game would be? $5. Because they like nice round numbers. They're not going to say the cost of this game is $4.50. Have you ever heard the term house always wins? Some of you yes, some of you no. House always wins is about probability, and it's the idea of if you find the long run expected winnings for each game, the cost of that game for any successful casino will always be greater than this. So that in the long run, the casino should always come out ahead. Does that make sense? See, I love that stuff. I think that would be fun. But no, I'm not willing to bet because, again, do not gamble because, again, I understand that in the long run, the casino comes out ahead. And in the long run, they do. In the short run, they may or may not. No. I like my job. Taking a bunch of teenagers to a casino, probably a guarantee that I would lose my job. Where are you coming from with this? My dog. That is my favorite animal. All right, guys, here we go. So I need you guys to think through this problem. This is what we just did. Here we go. Think through this problem. This problem is where now we're starting to get to the level of questions that I would actually give you. So please read this. Talk to each other. Work together on this. It's not that the math itself is hard. It's the critical thinking, the problem solving, and the critical reading that you need to understand. All right. Let's think about all the outcomes. What is, if I have a girl and the first child, what am I going to do? Stop. Stop having kids. You've reached perfection. Right, ladies? You're not going to have any more. What is the probability that you have a girl on the first child? 0.5, 1/2, 50%. I'm going to think in terms of 1/2 because it actually makes the rest of this go easier. So let's say I didn't have a girl on the first child. I had a boy. What's the probability of having a boy? 0.5. If I have a boy, but then I keep going because I'm going to go, right? I'm not looking for boys. I'm looking for girls. I really want the girls. So I have another child. What is the probability that my children are a boy first and then a girl? 0.5 times 0.5, 1/2 times 1/2, or 1/4. Okay? If I had a boy, but then I had another boy, what am I going to do? I'm going to do it again. So if I have a boy, and then a girl, I'm going to stop, right? What's the probability of having a boy, and a girl? 1/8. I just think it's easier because sometimes actually looking with the fractions is a lot easier. You're not rounding, you're not taking up as much space. But what if I had a boy, and then a boy? Am I going to go again? No, 3 is my limit, dude. Cutting it off. What is the probability of a boy, a boy? 1/8. So those are all of the possible, guys, those are all of the possible ways I can have children that meet this requirement. Do you understand what I'm talking about? Okay. Now, part A says create the probability model for the number of children they might have. So what are all the possible numbers of kids they could have? 1, 2, 3. Nope. 3 is by itself. For the probability model on that, what you're going to do is you're just going to say, okay, with the ones that I found, how do these probabilities work out? So, here's what I have. The only outcome, ladies, the only outcome that has one child is this one. So there's a 1/2 chance of that occurring. This is the only outcome possible for 2 children. So that is 1/4. 3 kids are both of those together, which makes 1/4. Okay, if you're confused, where did you get confused? Because for 3 children, I could do boy, girl, or boy, boy. So both of those outcomes fit into here, so I have to do 1/8 plus 1/8, which is 1/4. Or we could think about it this way. Do you agree that my only possible outcomes are 1, 2, and 3? Is that okay? Are you all right with 1 being 1/2? 2 being 1/4? No matter what, even if you don't like that calculation, what do all of these have to add up to? 1. So there's only one thing left for it to be. So the expected value of x, the expected number of children that I'm going to have, is 1.75 kids. Do not round that. We're not saying, you specifically at this moment, right now, what if everybody were to follow this philosophy, what would be the expected number of children that everybody would have? I'm not going to say Deo walks in and I'm going to say, Deo, you're going to have 1.75 kids. We're not going to argue whether or not that's just a very short child, or maybe a very, very, very tall child, or maybe a child with a birth defect and they're missing pieces. I don't care. Ladies and gentlemen, what's important that you understand here is that I'm not saying this is what is going to happen. The expected value is the extremely long-run average of what everybody possibly could get in this situation. Not what one person does, but the average of all possible outcomes. Does that make sense? Do not round. Now, the next question says, find the expected number of boys. Is it the same table? What is the smallest number of boys you could have? 0. What's the largest number of boys you could have? All 3 of them. So now my table And you see here I switched my variables. Now I'm talking about y. Because I've already used x, I'm not going to use x again. So y is the number of boys. I could have 0, 1, 2, or 3 boys. Well, that's actually the percentages that I have listed here. No boy, 1 boy, 2 boys, 3 boys. Just fill it out. So the expected number of boys is 0.875 boys. Again, it's not what I think is going to happen this one shot, but it's what I would expect to occur in the extreme long run on average. Okay? All right. I'm going to move on to the next problem. And ladies and gentlemen, just sitting there and kind of absorbing what we're doing here is not enough. You have to actually do these. Every problem is slightly different, and just sitting there thinking about the problem is not you actually doing the problem. So please, take this time to get the most out of this class. All right. Read through this problem. And reading through the problem is the most challenging part to understand what it is actually asking. Once you get it set up, the answer is easy to find. It's the setup that's hard. So my work for this one, you don't have to do a table. I did a table because to me, and don't worry about the pink, to me, the table makes it a lot easier to kind of understand. I know that there are two outcomes. I either lose $150, so that must be negative, or I gain $100. I will lose the $150 if my exam is scheduled on that last day. That's a 20% chance, which means that only leaves me with 0.8 for getting it right. So then you should have gotten your expected value to be $50 and your standard deviation to be $100. So let's think about that. The expected value. What does that mean? The average over the long term. So if she were to play this game and the probability stayed the same, in the long run, she would come out ahead $50 each shot. The reason why that's important is it helps you determine, is it worth the risk to you? Putting together the expected value and your standard deviation, would you take that risk? And that's what people should think about. It's not just, ooh, I could possibly save $100. It's in the long run, what would all of this stuff average out to be? If you think about playing the lottery, you can actually calculate the expected winnings for every single ticket. It's the same. And it's done by looking at all the possible outcomes. Now, the cost of one set of numbers for the lottery, I believe, is $2. What do you expect? What do you think the expected winnings are? Well less than $1. They make a lot of money doing that, which is why the jackpot grows so much. And there is a point in time where your jackpot might be big enough that your expected winnings might almost justify the cost of a ticket. But you have to think about those things. And that's what goes into a lot of this. Is it worth the risk? This is what happens to the average person in the extreme long run per game. Is it worth the risk? Okay? I wrote down here because I just want to keep pulling us back to this. Do not forget, if I were to have asked, instead of what is the standard deviation, if I had asked for the variance, you would have needed to take that number and square it. I'm going to keep coming back to that just to make sure we don't forget. It's a very important thing that you'll start seeing in the next couple of classes. All right. This problem here goes through a lot of different stuff. This is like all of chapter 14, and then some of chapter 15 is in here also. Read it through, think carefully, give it a shot. What you'll see up here, I have all of my probabilities calculated for A, B, and C. Check those out. Do we have any questions on those? Please remember, you cannot just say, no. That is not good enough. Yes. So if you could have said no, because the probability changes whether or not you won the first game, that's perfectly fine. That's perfectly fine. Okay? But we got these two okay, right? So if we're talking about the number of wins, let's use these values to finish off this table. Lose means how many wins did you have? 0. Any other from 2 games? No, so I'm going to put 4.42 here. Win. How many games did you win there? Are there any ways to win? The 0.08 there. What should be true? It equals 1. What am I missing? That's it. I mean, you could have, if you wanted to, think about, I could have lost the first one, lost the second one, lost the first one, won the second one, won the first one, won the second one, won the first one, lost the second one, and calculate each and every one of those probabilities. That's a lot more work. It's a lot easier to just say, hey, I'm going to find the 2 easy ones to calculate. I'm just going to subtract that all from 1 to get the one I'm missing. If that's the case, what does your expected value end up being? 0.66. Not games, we're wins. And my standard deviation, and again, wins. Doing a little bit better with this? This times this, plus this times this, plus this times this. And then really it was just in the calculator, because I don't want to calculate standard deviation by hand. You could have done a tree diagram. Okay. I'm going to have one more problem for you all. Last problem of the day. Go for it. So for this problem, the way I handled it, I understood that I'm looking for, since we're talking about expected number of good ones, and good batteries is what we're talking about, the number of good batteries I could have was either 0, 1, or 2. To finish my probability table, I need to understand where these numbers come from. Now, if you look at the way the textbook would work this out, you can do it this way, where you do all of the math in the box as well. I don't like doing, sometimes I'll do that. It depends on how much space I have. You can write it separately. You don't need to show the work for every single probability. If you have 3 spaces, you need to show the work for 2 of them. The third one is just whatever you're missing to add up to 1. Okay. Probability of no good batteries means they're both bad. So 3 are dead. So 3 out of the 10, take 1 out. Now there's 2 bad left. 2 out of the 10, out of 9. Both of them good. There are 7 of them good. So 7 out of 10, take 1 out. Now there's only 6 good left out of the 9. Work that out. Okay, the bell is going to ring very shortly. Ladies and gentlemen, we are at the point where you can do the first piece of the Khan Academy for this set. I will try to answer quiz questions next time because we ran out of time.